Hi guys, Professor Burns here. We're going to take a look at section 7.4, which is where we get into the inverse of the Laplace transform. And you'll start to see, again, it seems a little bit abstract. Why are we doing this? What is the Laplace transform for? Why do we need to know what the inverse is? In the next section, it'll all kind of come together, and you'll see how we put together these properties and this inverse rule for solving differential equations using the method of Laplace transforms. So for now, again, as I've been saying throughout the whole chapter, just kind of go with me on this, and we're going to look at how we find the inverse of one of these transforms, so going in the opposite direction. Given a function f of s, capital F, if there is a function little f of t that is continuous and satisfies the function Laplace of little f is equal to big F, then we say little f of t is the inverse Laplace transform. Notationally, and I generally use this notation with the -1 because that's the inverse notation we're familiar with. We do Laplace transform of, and call that the inverse of the original function. And by the way, I just noticed in the notes that this L and this L look different. Don't get confused. That was my equation editor. It's the same thing. It's that script L for the Laplace. So let's do a couple of examples and just look at how we would figure these out. For most of these, you want to match them to something that's in the format we need for one of the functions in that table I gave you in 7.2. Remember, I kept saying we're going to go back and forth to that table. Let me just quickly show you what I'm talking about. Let me click on it here in the notes. This table right here, and let me get rid of the writing that's here. But for a lot of these, we're going to match them to one of these forms and use that to help us work backwards to get the inverse. So for this first example, we've got 2 over s cubed. So we want you to observe that 2 is really the same thing as 2 factorial over s to the third. That's s to the 2 plus 1, where n is 2. And notice that that is in our table. Let me go back to it here. Right here, n factorial over s to the n plus 1. That's t to the n. So in this example, n is 2. So this just means that the Laplace inverse of Laplace for 2 over s cubed is just going to be equal to t squared. And that's it. That would be the original function that produced that Laplace transform. Take a look at letter B. We've got s minus 1 over s squared minus 2s plus 5. So this doesn't at first glance look like one of the formats in our table. And what you'll find though is that a lot of these where you've got, if it's s squared plus b squared, it's probably going to be a sine or a cosine function. But if it's got 3 terms, what you want to do, and it's a quadratic, what you want to do is look to see if maybe you can complete the square and get it to match one of these terms. So let's try that. Let's go back and let's complete the square on this denominator. So as a reminder, how do we complete the square? Let's make sure we remember how to do that. S squared minus 2s plus 5. Obviously that doesn't factor. Of course, if it does factor, you can break it down, but this does not. So I'm going to complete the square on the 2s. So that means I've got s squared minus 2s. Remember how to do that. You take that -2, you divide it by 2, you get -1, you square it, you get +1. So that means that if I add a 1, that will complete the square. But I can't just arbitrarily add a 1. I have to also subtract the 1, or I've changed the value of that expression. So that means this is now s minus 1 squared plus 4. And that's really what you have there. So we're looking for the inverse Laplace of the expression s minus 1 over s minus 1 squared plus 4. So let's go back to our table here and see if that fits one of the forms we need it. And it does. It looks to me like it is this format where A is 1 and B is, I think, 2. So let's go back. Let's see. Yes, A is going to be 1 and B is going to be 2. So this becomes e to the at, so just e to the t times the cosine of 2t. And that's going to be your inverse of that Laplace transform, or inverse Laplace transform. Let's do one more here. 3s plus 2 over s squared plus 2s plus 10. Again, we have a quadratic in the denominator. I don't think it factors. So let's go ahead and let's just try completing the square and see what happens. S squared plus 2s plus 10. If we complete the square, that gives me s squared plus 2s plus 1, right? We complete that square, plus 10 minus 1 to balance it out. So we end up with s plus 1 squared plus 9. So what we have is we have 3s plus 2 over s plus 1 squared plus 9. I'm going to separate this and write it as 3s over s plus 1 squared plus 9 plus 2 over s plus 1 squared plus 9. Now here's where this gets a little bit tricky and where you've really got to pay attention to this table. Let me go back to it again. We've got, let me erase my writing here, we've got s plus 1 squared plus 9 in the denominator. So that leads me to think, okay, it's going to be one of these two formats, but with the sine function, I need just a constant on the top, and specifically it needs to be b, whatever that is. So in my example, b is 3, don't forget. Let me write that just as to reiterate. Let me go back. Here's what I had. I had 3s over s plus 1 squared plus 9. Plus 2 over s plus 1 squared plus 9. Okay, so let me reiterate what I'm talking about here. So we've got, for the sine function, this number and this number need to be the same. So there's a constant there. So if I have a 9 here in the denominator, whoops, let me fix my screen. If I have a 9 here in the denominator, then, sorry, it's getting a little bit messy. I want to make sure you see what I'm talking about, though. One more time. All right, there's a 9 right here. That means that this number needs to be what? In order for this format to match, this number needs to be a 3. In this example, on the other part of it, I've got a 9 here, but now look, I have an s. Well, that leads me to think it's going to be this format because there's an s, but it can't just be an s, it needs to be s minus a. So here I need to somehow get s plus 1 in this expression. So that's what I want you to keep in mind. Let me go back to the example here. Let me write that down again. So we've got, let me write down what we need. We need this 3s over s plus 1 squared plus 9 let's do it this way. Let's do 3s plus 2. Let me write the whole thing. Equals, we need this to be something, I'm going to call it a, times s plus 1. That would be what the first term needs to turn into. The second term needs to turn into a 3. So I'm going to call it b times 3. All right, let me clarify what I'm doing because I know this is confusing. It's almost like I'm matching up a one-to-one correspondence. So I need that first term to contain an s plus 1, and my job is to find out what I need to multiply that by, what this a needs to be to give me an s plus 1 here. In the second term, I need this to be a 3, so my job is to find out what to multiply by to give me a 3 in that numerator. So what we're going to use now is the method of partial fractions. I know you remember partial fractions. We've done it. We did it in this class earlier in the semester. I'm going to multiply through by the common denominator, and I wind up with 3s plus 2 equals a times s plus 1 plus b times 3. So then remember, you can choose, this has to work for any values of s. So I'm going to choose s equal, I always like to start with 0 if I can. That gives me 2 equals a times 0 plus 1, so just a, plus 3b. So that's one of my little equations here. And then let's suppose that s equals -1. If s is -1, what happens to this a term? You can see that it's going to go away. So I have negative, let's see, if s is -1, 3 times -1 plus 2 gives me 3b. And if you solve that now, you wind up with b equals -1/3. So now you have b, you can go back and plug that in to this equation and solve for a, and you'll get a value of 3. So let's put all this together. We're looking for the inverse Laplace of the function a times s plus 1. Well, we just said a was 3, so 3 times s plus 1 over s plus 1 squared plus 9. And then remember, Laplace transforms can be split up, so can the inverses. So I'm going to write the second one on its own, the inverse Laplace of b times 3. So that's going to be, let's do -1/3 times 3 over s plus 1 squared plus 9. And remember, this 3 can be moved to the front. It's like a constant multiple. Same thing with this -1/3. So we wind up with 3 times e to the -t cosine of 3t. That's the first expression for here. And then plus, actually it's going to be minus -1/3 times e to the -t sine of 3t. And I promise we will do some more practice with this in class. I know this is a little bit tricky, this method, but the idea is you want to try to match up whatever you have here with something in that table. And it might require a little bit of algebraic manipulation, and that's what we did here. This expression, 3s plus 1, plus or minus 1/3 times 3 over that common denominator is equivalent to this. It's the same function, just rewritten in the format we need it to be. So make sure you bring your notes with you to class. Try not to be absent. This is a good one to be there for, and we will do plenty of practice with this tomorrow. So I'll see you then.